You're listening to the Thesis Review podcast. I'm your host, Sean Wellick. I'm a PhD student at New York University, and my research focuses on machine learning, natural language processing, and structured prediction. On the Thesis Review, I'll interview researchers from around the field, centering the conversation around their PhD thesis. In addition to exploring the technical content, this will give insight into their history as a researcher, allow us to revisit older ideas, and provide a valuable perspective on how their research and the field itself has evolved since their PhD days. My guest today is Julian Togelius, who is currently an associate professor at New York University's Tandon School of Engineering, where he co-directs the NYU Game Innovation Lab. Julian's research is at the intersection of computational intelligence and computer games. In short, he researches what AI can do for games and what games can do for AI. His PhD thesis is titled Optimization, Imitation, and Innovation, Computational Intelligence and Games, which he completed in 2007. We discuss his work in the thesis on AI for games and games for AI, including methods such as evolutionary algorithms, issues such as generalization, and applications such as personalized content creation. That's right, you can picture Mario Kart creating unique tracks that suit aspects such as your own playing style. We talk about how this connects with his recent work on procedural content generation, and he gives some great advice on how to pick problems, differences between AI for games in academia and industry, and more. The Thesis Review is available on SoundCloud, Apple Podcasts, and Spotify. And be sure to follow us on Twitter at Thesis Review. If you would like to support the podcast, you can buy me a coffee. I'm not joking. You can go to buymeacoffee.com/thesisreview and contribute $1 towards coffee funds. And now, here's Julian Togelius with Optimization, Imitation, and Innovation, Computational Intelligence and Games on the Thesis Review. Your thesis begins with, once upon a time, it was widely believed that we could build artificial intelligence ourselves. So I wanted to get your current view on this. Do you think that we could try to understand intelligence in enough depth to construct something, or do we need to construct a system that actually learns to be intelligent?
Oh man. Wow, hitting hard. So first of all, Once Upon a Time is because I wanted my thesis to read like a fairy tale. I wanted to start with Once Upon a Time, and I wanted to end with, and therefore they lived happily ever after. However, I didn't come up with a good way of making it end that way because I don't know that they would live happily ever after, like the neural nets or whatever. Yeah, so do I believe that? I think my after like working with a bunch of like true AGI believers, most notably my postdoc boss Jürgen Schmidhuber, but also others, and like being confronted with those and reading up about that, my position has changed to the strange position that there isn't such a thing as general intelligence. There's a bunch of cognitive capacities of different kinds that we can have, and we as human beings are very complex hodgepodges of different mechanisms that interlock in different ways. And it's more general than basically anything you can find out there today. There's more general than any kind of intelligence we built. But there's probably, it's probably covers, our intelligence probably covers a very, very small part of the space of possible intelligence that we could have. So I have sort of evolved to the point where I think the question of general intelligence is sort of meaningless. Still, I'm working on it.
I
So
see.
I don't.
Yeah.
I think that for basically any question we can formulate precisely enough, we will relatively soon be able to come up um, uh, with technical. We will be able to build technical systems that can get there and solve it. But I don't think that the question of intelligence with like capital I don't think we're anywhere near understanding what we're even asking for.
I see. But maybe for certain types that we define, there's there's some hope that we could understand it well enough to build something,
Yeah,
maybe.
definitely, definitely.
Yeah.
That's why. That's why I don't know if I'm jumping ahead of time with things here, but let's so we prefigure the discussion. That's why I'm working on games,
Mm-hmm.
because they're so widely diverse. There's so many different cognitive challenges in games, and they're well defined. It's beautiful.
Mm-hmm. Yeah. So maybe let's go to before the PhD, actually. So were you more interested in artificial intelligence or games, or going in, did you know that you wanted to try to investigate both of these at
Well,
once?
so yeah, I mean, the path is essentially that I finished high school,
Mm-hmm.
despite being very, very bad at maths, I and I had people in my class who wanted to be engineers and study engineering, and I was like, I looked at them and like, I do not want to be like them. I'm a philosopher and a poet, and I am going to study philosophy and psychology and understand the mind, and have great philosophical thoughts. So I started with that, and I mean, I got to the point where I was being asked if I wanted to apply for PhD in philosophy. So
Mm-hmm.
I dodged that bullet. Um, I, I gradually realized that um, I mean, I wasn't going to make much progress there. I mean, only a few people actually make real progress in philosophy every generation or so. That's at least my sort of partial outsider view. But and I didn't, which is when I was too impatient. So I gradually drifted over into computer science. It helped that I was one of the kind of people that have taught myself to program from basically trial and error back when I was 12, 13 years old, and
Mm-hmm.
hacking away with Turbo Pascal. So I got into computer science, and then I didn't still didn't want really want to be a computer scientist. So I went into um, uh, I took a master's in evolutionary and adaptive systems, where the idea was to sort of biologically model intelligence from the ground up, starting with snails and crickets and stuff like this, and then eventually we'll get to dogs and presidents and human beings. And then we didn't really sort of, yeah, yeah, the core idea there was that we could basically use evolutionary computation, which is basically Darwinian evolution, to evolve intelligence and using robots as our test bed. So I was very much into that paradigm for a while. Did my master's at University of Sussex, and I was the original question that animated me was like, what is consciousness and how does it relate to intelligence? But I was also interested in intelligence as such. So for a while, I was very much into the sort of bio-inspired theories of intelligence in cognitive science and activism, and now I forget all the words here,
Mm-hmm. Yeah, yeah.
homeostasis and so on. Um, and and I thought that was going to work in that paradigm, evolve robot controllers. What happened when I started my PhD was that I figured out that robots were just far too slow, and um, uh, you say that you need to test this strategy. I mean, you basically need to test 100,000 different strategies in order to find a good one in evolutionary computation. Well, too bad that you have to watch this robot do this 100,000 times, and you have to basically be there and nurse it and change its batteries and wait until the tires cool down and all kinds of things. Change oil. I did a bit of
Mm-hmm.
that research. I worked together with Renzo Donardi, one of my good friends from my PhD, on evolving neural networks for controlling miniature helicopters. And we worked in simulation, but we still needed to work to use the simulations to test the simulation of real robots, and his room was actually littered with broken toy helicopters, which was kind of fun. But I mean, research doesn't really progress very fast that way. it's,
Mm-hmm.
so that's how I got into games.
Right, yeah. Yeah, you also brought up this in the thesis, you mentioned this issue of like recoverable versus non-recoverable. So in robotics, um, or if you had a car, for instance, and it crashes, then you can't just reset the car to some new state
No,
and run another trial.
no.
Yeah.
We're not in the world that Elon Musk thinks he lives in. But yeah, no, wouldn't
Yeah.
it be great if we could just run all this physical simulation, just reset the world? But yeah.
Yeah, yeah. And yeah, so then the title of your thesis is Optimization, Imitation, and Innovation,
Mhm.
Computational Intelligence and Games. So I guess eventually you did choose to focus on games, and you start off with this really nice taxonomy of those three things, and then
Yeah.
also this kind of duality of AI for games and games for AI. So do you maybe just want to talk through that a bit?
Yeah. Yeah, no, definitely. Because this is not quite the sort of, the taxonomy I sort of operate in, but it's still sort
Mm,
of related. I sort of taken it further, but the idea when I started was that when you had, I mean, started my PhD in 2004 in October at the University of Essex in good old Britain. And back then, very few people used video games for AI research.
mm,
And it was like it wasn't a research field. Of course, people had been working on chess since the 1950s, and people had been working on Go since not long after that. And there's been lots of progress in checkers and even then like simple versions of poker and so on. But video games wasn't really a thing for AI research. There was a few
mhm,
scattered papers. And my advisor was actually part of setting up the first conference on that. My advisor, Simon Mark Lucas, at Essex, now at Queen Mary in London, setting up the first IEEE symposium on computational intelligence and games. And we were talking about whether we should move into that space just when I started. I was very
mhm.
receptive to it. Now, I mean, of course, I need to mention somewhere, but yes, I always liked playing games. So, video games in particular. Um, uh, then there was this, there were all these people doing AI for the game industry. But AI for the game industry back then, in particular, and to some extent still, was very, very different from anything we call artificial intelligence in academia. It was basically
Mm,
application of A star derivatives and finite state machines to create quite heavily scripted human-like behavior in non-player characters.
mhm.
It's That's not quite all there is anymore, but this is still sort of the foundation of it, of what's often referred to as AI in the game industry. So there are people doing AI for games um, with that motivation who are completely uninterested, aggressively uninterested, like you know, very loudly uninterested in what went on in academia, and went out of their way to tell us that what you're doing in universities is bullshit. So this you still find a little bit of this attitude in some game developers, but mostly this has gone away. Thank you. I mean, I'm yeah, happy for that. so uh, but then there was these sort of the attitude from the people who basically worked on chess because chess was all there was. This was like the this was the crucible of intelligence, and that's why we're working on it. So I've tried to navigate that space, and it was really tricky because I was neither of that. I thought that like video games had a lot of cognitive challenges, different from what you had in game in in classical board games, such as chess and Go, but also that AI could be useful for games, but maybe not in the ways that you think. Maybe not in terms of like creating a really high performing enemy in a game, because that is rarely particularly interesting for a game developer. So
Mhm.
that's why I sort of made that distinction. And then I proceeded on working both on AI for games and games for AI at the same time, because it's connected, but they are different things. So
Yeah, I
yeah.
see.
So the optimization, innovation, and imitation, I was talking about like optimization is mostly like trying to make an agent that performs well in a game.
Mhm.
Imitation is trying to sort of imitate some kind of human playstyle, and innovation, the way I sort of used the term back then was about using AI in very non-traditional ways in games, in particular for what I sort of started with that paper from 2006 and then 2007 paper, using modern AI for generating game content.
And then games for AI is kind of the summary would be that it just provides a good test bed for testing ML systems or trying to push them further. Is that
Yeah,
yeah?
ML, and not only ML, but also because people these days tend to think that all of AI is an ML,
Hmm.
which is not true. Also, optimization, tree search, and possibly reasoning and stuff like this. So yes, AI as a testbed for AI systems of various kinds. Well, games as a testbed for AI systems of various kinds.
So then you said that nowadays you might modify this taxonomy.
Yeah, I mean, I've been doing several attempts at coming up with new taxonomies. The most recent update is probably in my book with Yorgos Yanakakis, where we are um, trying to. This is from 2018. It's just called Artificial Intelligence and Games. We divide the use cases of artificial intelligence in games to into playing games, generating content, and modeling players. And then we have a couple of
Mhm.
subdivisions in here. Playing games in particular is subdivided into where you're playing as a player or as a non-player character, and are you playing it in order to win or playing it for to recreate some kind of experience. So
Mhm.
all of the stuff you get where people use games in a very narrow sense of test beds, like the DeepMind and playing Atari and so on, and for the or for that that matter AlphaStar and so on, is about playing games as a player, so in a player role, and playing it to win. Now there are lots of other different there's lots of other different ways of playing games, lots of different purposes.
Mhm.
Optimizing generating content can also be done for different purposes and different trade-offs, and then modeling players. You can model player behavior, model player experience, and many things. There are other things that are definitely in the AI in games sort of field that don't fit neatly into this. In particular, trying to learn forward models or model game engines, which is like a, a sort of growing area where people are trying to sort of get models of game engines, various degrees of fidelity is one thing,
Mhm.
and there's a bunch of like complicated analytics that is being done uh, in industry that don't neatly fit into here into that either. Where you're sort of trying to analyze larger patterns of gameplay. Interestingly, the area where you see most modern algorithms being used in the game industry currently is in analytics, where you're trying to sort of
Mm.
because basically any game developing any game development company will have instrumented games to send lots of data back, and then they're sort of trawling through this to figure out how they can make more money in some way.
I see. And then I guess you kind of touched on it. So then the relationship between academia and industry, do you think that nowadays it's maybe like lagging behind, but they'll eventually pick up the most innovative methods, or is there still kind of a divide between the
It's
two?
gotten better. It's gotten better. I had like I remember some of my early sort of interactions with the game industry back in 2006 or so, and people had the most weird ideas about what we were doing with AI and so on. But it's definitely gotten better. Oh, I remember going to meet Microsoft research, Tori Grapple, now at DeepMind, and Ralph Herbert, now at Amazon, who was at Microsoft research, who had done the drivatar system for Forza Motorsport for the original Xbox, and also the what's it called? Some other work on doing using RL to play fighting games, and I was really impressed. And I showed them their work. They showed their work. We talked about whether I should go there for an internship, but didn't end up happening. But and I talked about asked why this Dravatar thing, which is like actually in use in a real racing game for which played by probably millions of people. It would model people's driving behavior, and so you could basically send an avatar of you driving over to someone else and race someone in their place. Why didn't you publish this in a big AI conference? And they were like, nah, we're sort of ashamed of sending it there. It doesn't have enough math. Which is like, that problem has not gone away, by the way, with the bizarre reviewing standards at main AI conferences. That has probably only gotten worse. But that's not what we're talking about here.
Mhm.
So these days it's much better. It's happened in a very strange way because basically there is a group of people doing game AI and are game AI programmers who tend to be pretty conservative in what counts as game AI, what are like the proper methods, and what are the proper reasons for doing this.
Mhm.
And they have not, in general, with exceptions, of course, been very welcoming towards the AI revolution, the deep learning revolution, and things around that. I would say, from a game perspective, there's a deep learning revolution with deep RL and deep networks in general. And there's another revolution which is equally important from a game playing perspective, which is the Monte Carlo tree search revolution,
Mhm.
which people who people who think that AI is essentially ML may have sort of missed the extreme importance of the invention of Monte Carlo tree search, which was in 2006, 2007,
Mhm.
and the various derivatives and improvements on this basic framework that has made basically control and planning tasks in tasks with very high branching factor and uncertain rewards possible to like a
Mhm.
completely unprecedented amount. Anyway, so there are people that are receptive to this, but that originally didn't come from the gameplay programmers. That came from management. So basically, people
Mhm.
higher up in these game development companies looked at all these newspaper articles about, oh my god, people are using deep networks and all these things all over the world in industries from aerospace to I don't know accountancy or things like this. I'm not sure about accountancy, but it's probably true. and then, and then they're like, wait, why are we not doing this? We're like, a game developing company. We're supposed to be high tech, aren't we? So it's switched around, but it's still there's still a
Mhm.
lot of gap to be closed. That's also why I started this company. So together with some of my good collaborators and some previous students, we started up a startup called Model AI, MODL.ai, where
Mhm.
we do um, try to commercialize various ideas that come from research in game AI and try to build products for the game industry that improves game development in various ways.
I see. Yeah, that makes sense. Whenever there's a gap like that, I start thinking maybe there's a startup opportunity.
True, and we're not the only startup in that space, but I guess we're the most comprehensive of them. But yeah, it
Mhm.
is true. I'm actually involved in another startup. I'm advising one of my students in a startup on AI in the energy sector, first applications in oil production, and this is also a field where basically they have a lot of technical knowledge, but not in AI. So, you can get very
Mhm.
far by basically reading research papers from a few years back and like, aha, this applies.
Yeah, going back to the thesis. So, as I was reading through this, one thing that was interesting is that if I listed off some of the methods that you use or the topics, like evolutionary methods, reinforcement learning, neural networks, all of these things seem very relevant still
Yeah.
now. And so I was curious, like at the time, how did you land on using these methods? I mean, maybe these three, so evolutionary neural networks and then reinforcement learning, and how did they seem suitable for games in AI?
Yeah, it's funny because I mean we've seen lots of advancements in all of these fields, though the ones that get talked about are in reinforcement learning. Where
Mm,
I mean, when I started my PhD, if you want to talk about reinforcement learning, you basically went through Sutton and Bartle's book, and you talked about the proofs that in some very rare cases, Q learning would converge, and then
Hmm.
and then you'd have your students ask you, okay, but can you tell me where this is actually used? And then you would mention Jared Tesauro's TD Gammon, where he used temporal difference learning to learn to play backgammon, and actually the network got really good at it. And then, okay, more. Tell me something that's not backgammon. And then you were like, that's a good question. And then you would remember that Andrew Ng had recently put out some really impressive work in using off policy RL to control helicopters, and you mentioned that, but you wouldn't really understand how it worked. but, but I mean, back in 2004, there were extremely few examples of reinforcement learning actually working. It's
Hmm.
so the thing that happened basically in 2013, 2014, when DeepMind put up some early preprints, and then that with a Nature paper in 2015, that was like sort of it sort of set off an explosion, really.
Hmm.
So it's very relevant. The reinforcement learning problem setting is very relevant for games. Now there are many ways of approaching it. For a long time, I mean, people have been using evolutionary algorithms to learn to solve reinforcement learning problems for a long time, probably way longer than they have been using things from the temporal difference learning family. And there's been this weird ideological divide where basically a lot of people from the reinforcement learning field would look at these successes with evolutionary algorithms and say that, well, that doesn't really apply because they there is no theory to show that they work, and there's not enough math, and they should be really inefficient. And these examples of them actually working must be some kind of fluke or something. So I'm happy to see that that has also changed in recent years. So
Hmm.
basically, OpenAI's paper will use a strangely simplified or impoverished version of the natural evolution strategy to with good results, showed that it was
Hmm.
extremely parallelizable. And then several people independently, including the Ken and Jeff at the Uber AI and Joel at the Uber AI labs, I'm showing that evolution strategies and policy gradients are sort of variations on the same theme. So you sort of see
Hmm.
that it's not like an ideological divide. It's a continuum where you have versions of these algorithms. This has made me happy because basically it
Hmm.
shows that, like, we can talk about this like reasonable adults again, about the advantages and disadvantages of different kinds of learning. I find this extremely fascinating. I think casting game problems as reinforcement learning is very useful. We have a new paper, which is under review now, but it's been in archive for a while, where we show that we can cast procedural content generation as a reinforcement learning problem as well, and actually get
Hmm.
really fascinating results on that. So all that is really cool, but there's also very many different ways of casting problems that are not reinforcement learning.
Hmm.
That's And the way my mind works is that if lots of people discover a problem and try to work on it, I move away from it. So nowadays, I'm mostly interested in things that are that are not easy to stuff, or like weird corner cases where like the reinforcement learning problem formulation is does not really work, and so on.
Hmm. Yeah, we. I was just at a NLP conference, ACL,
Yeah,
and the keynote speaker had this good line, and her advice was, "When others go north, go south."
yeah, yeah. That was completely true. Completely true. I saw this discussion on Twitter the other day about, like, someone, like some poor master student or something. Oh my God, how can I get into machine learning? It's so high competition. To get into a good program, you already need to have papers and stuff like this. And yeah, so my advice is that don't get into machine learning. Find another problem set that has something to do with machine learning, basically. But like work. I mean, figure out like a problem in some field, and then like this intersects with machine learning, and then sort of start from there. Um, or like find something that basically does machine learning is not likely to work on at all, and figure out what works instead. It's
Hmm.
there is this idea that applied research is somehow less worth or something, but I think the question of what's applied and what's core is very relative to your to where you come from and your preconceptions, because I think there's a lot of applied research gives us new questions, and
Hmm.
they are like um, and they can be just as much worth and just as central to something as the so-called core questions. So yeah, I totally agree with that keynote speaker. And when I say that the reinforcement learning formulation is very useful, I I do not think it is in any way kind of ontologically more primal than other questions.
So it almost seems like you followed this your advice in a sense, because at the time applying uh, these methods to games was kind of new.
Yeah,
Do you also think that kind of simultaneously using the evolutionary methods as well as others? Because I know like historically there was a divide in the community. Do you think that
yeah.
was valuable for yourself as a researcher?
It was definitely valuable to be doing something that other people were not doing. I think that
Yeah.
was. I have like to sort of to bear my inner deep insecurities. I've never thought I would be very good at joining a field where other people were doing something, and then I would have to compete with lots of good people on doing that. That's not where my strength is. And partly because I really don't know much math. I really don't, and I find it really complicated. And partly because like I don't know, I see people that are like in traditional terms just like smarter than me all the time doing these things. However, I am good at scouting out things that are new, and I
Mhm.
sort of have this kind of attractor. I'm like if other people are avoiding a topic because it's complicated and self-contradictory and doesn't make sense, and I'm sort of drawn to it. Like, aha, there's something here. it's
Mhm.
um, I sort of I like the complication and the sort of lack of good good way of lack of good problem formulation.
Yeah, well, this was really good. Turned into a really good advice.
I don't want to say that everybody should do like what I'm doing or what I did. You should do it if you function sort of like me. I mean, there's also lots of people who don't function that way. Lots of people who really just thrive better on like having a well-defined problem and just hacking away on that because that's their skills, and that's fine. That's great. We're all different.
Yeah. I think throughout these interviews, I've been trying to ask each person kind of where do they get research ideas from? How do they pick research directions? And so
Right.
it has been interesting to see how each person kind of has a different
Yeah.
opinion and suggestion.
Different
Yeah.
meta level strategy, right? For
Yeah.
this.
Yeah.
Yeah. Yeah. No, I think it's true.
Yeah. So let's go to, well, one part of the thesis, which was on optimization at a high level. And specifically, there you looked at this car racing task. So this
Yeah.
game that
Yeah.
you made yourself.
Yeah. No, my advisor had this like Simon Lucas. He had this table with a simple sort of racing track and then he had two like radio controlled cars. These old ones you can buy for like $10 or something, and then we would drive them around the track, and it's surprisingly hard because it's so fast, and also because you need to sort of put yourself. You basically need to do this mental transformation of being in the car and making sure that the turn gets right all the time. Somehow you can do it, but it's not obvious that you should, right?
Yeah, and then so here you were looking into a few things. So first is just can you evolve or can you train a model to work on a single track,
Mhm.
and then eventually can you train it to generalize or to work on multiple tracks?
Mhm.
Yeah, could you just talk a bit about yeah, like why you set up this racing car? Were these the things that you wanted to investigate with this set of experiments?
I mean, originally it was Simon's idea that I go into. go into car racing because he thought that these cars would serve as a good vehicles for my research, pun intended. Um, and and for me, I can never say no to a good pun, so I did that. No, but I saw the reasoning. So it's um, uh, yeah, it's a control problem. Driving a car around the track is a control problem that initially seems simple, but then you remind yourself that lots of people watch other people driving cars around the track, and it's extremely satisfying and exciting for lots of people. And like some people spend all their lives on this and don't get as good as other people who spend all their lives on it. Aha. So it cannot be that trivial, clearly. If it was trivial, we wouldn't have the car racing would not be a sport, um, um, just like football or whatever. So, and you can divide it up into different tasks. There's like you have this task of fine motor control, and then you have fine motor control. And when you drive around the track, then you also have a planning, And if you have multiple cars on track, you have adversarial planning. And yeah, I'm trying to learn to. I'm 41 years old and I'm trying to get a driving license now in New York City. And there's a lot of adversarial planning going on. It's like,
Yeah, yeah, yeah.
it's not trivial. So we decided to set up this problem in a sense that this was also like, as a holdover from my robotics days, that I wanted to be able to drive this. I wanted to train neural nets that would be able to drive these cars um, based on egocentric sensors. So basically, sensors that could have been put on the actual car. And I use these like simple rangefinder sensors, also inspired by what you find in simple research robots like the Kepler robot and so on. I did some comparisons and figured out that if you gave it like third person inputs, like where are you on the screen and so on, then it wouldn't work as well at all. It was much harder. In fact, I did some work where I tried to learn to drive from pixels, which was much harder. I got some successes, but not very good, not very good successes. And I thought that this is a stupid problem formulation. Fuck this. And then later on, this would become like the main problem formulation for sort of arbitrary reasons. But yeah, it's but I was working with egocentric sensors. It works much better because the perspective an organism have when it perceives the world are extremely extremely important and basically shapes what it can do. In in terms of ecology, it's called the yeah it's called having certain affordances. I trained neural networks that drive around the track, and then I was happy, published a paper, and got very good response from the community. So I sort of set off trying to do this on more different tracks, and I figured out that no, it doesn't work because if you train it to only drive one track, it won't drive another track. Then I decided that, well, there must be a way of doing that. So I used incremental evolution, which is the same idea as is now more commonly known as curriculum learning. I tend to be of the opinion that all good ideas are are invented multiple times by multiple different people under different names, and that's just a sign that it's a good idea. This is a way in which I am, by the way, disagreeing with my old mentor Jürgen Schmidhuber, who tends to think that something was invented only once, and other people who invented it later have sort of ripped off that invention. Not, that's not a completely fair representation of his stance, but something like that.
Yeah, yeah.
Yeah, so basically, I trained it so that, for when we learned to drive on one track, you added another track to the fitness function. So now it was evaluated on its capacity to drive two tracks, and then you added a third track, and you added a fourth track, and so on. And then you added some really, really hard track. And I could show a number of things that, for example, if you have only one track, and you even try to make it drive the same track but backwards, so you have to turn right instead of left, it just won't do it. It will just crash. You hyper specialize. And if you then add more and more tracks, you can gradually get better at driving it. And then you can learn to some very complicated driving behaviors. And you can learn to, because you can sort of prime it with what is learned on the previous tracks to sort of learn, so that you can learn to drive really complicated track that you could not learn from scratch. Which was really nice. I like that work. And this is something that I am still, this perspective still informs me, because we still see this thing going on in reinforcement learning. So in reinforcement learning research of today, the sort of standard setup is to use pixel input. And then you learn to play a game, some Atari game or something else. Most of these games have a sort of third person viewpoint where you are, or you control a little character on screen. I am of the firm belief that what is learned in this setting is not at all a general policy, in fact, extremely far from a general policy. It is not learning to play the game, it is learning something like a lookup table that in this data take this action. And while I don't doubt the literal words of, like, I don't doubt the actual results of all the work in deep reinforcement learning and pixels. I do think that this work is in some sense a lie, because you are not learning to play the games. You're not learning to play games in any sort of generalizable or transferable way. And people are trying to mitigate this in various ways and looking at it like, that's a small technical problem. But I think people are not really seeing how extremely deep this problem goes. We do not currently have a way of training a neural network to play sort of a standard Atari game in any kind of general way. And when I mean general, is that it should be able to play it from different angles. You should be able to play it from different different levels in particular. So we did some work over the last few years. We did some work where we looked at, can you train either with evolution or with A to C or DRL or some DRL derivative. Any of the standard sort of deep reinforcement learning algorithms you find in the standard toolkits these days. If you're training to play one level of a 2D game, which you view from above, and then give it another level, will you solve it? Answer is no. Completely no. Always no. How can you train a policy that can actually play any game that is in this form, or any level of the same game? The rules are the same. Say, for example, you need to grab the sword, kill the spider, and go to the door, in a simplified version of Zelda that we're using a lot. But you need to do this in all these levels that have different geometry, and the door is a different place, spiders come in different places, and the key is in different place, and you start in a different place. Still, the logic is the same. You can easily use a standard tree search algorithm, such as Monte Carlo tree search, to do it if you have a forward model. Can you train a neural network to do it? No. They just don't. Yeah. You can make slight advances on it. And we've been using a lot of this thing, generating new levels, training in more and more generated levels to make it slightly better, but we have a long way to go there. So this completely, directly harks back to the research I did on evolving general driving behavior back in 2006. Except that I made it very easy for myself back then by having sensors that were centered on the car. If you basically make it from a third-person perspective, it's much harder.
Yeah, so the generalization hasn't been solved.
Not at all. Not at all. We're barely even making progress. It's like, I think people are not... and you tell this to people people from the media, they would be shocked because everything they hear is that now look, we already have these really strong game playing agents, and this is all solved basically because that's the story that's been sold essentially. And then,
Yeah.
yeah,
Do you have an intuition for how we attack the problem? Like, do you think it's something inherent in using these neural models, or does this maybe relate to your work on trying to do this content generation, where maybe if we train on a diverse set of environments, then that could promote generalization?
yeah. I think content generation is a crucial and necessary part of it. You can't just. I think that's also why Atari is sort of dead. We should move on because all these games only have a set number of levels in the same order. Um, uh, Whereas, so we need environments where we have procedural content generation. So we did a lot of stuff with the general video game AI benchmark that we created,
Mm.
and OpenAI, partly following up on this, have their ProcGen benchmark that is really useful for this, with a lot of small games where they have lots of generated levels for those. Um, I was also participated with Unity in creating this obstacle tower challenge, which is also procedural generated, but with a very nice high fidelity graphics input. So procedural content generation is a crucial part of this problem. However,
Hmm.
I think we need more. One thing that bothers me is the tiny size of the networks we use here. And this is also maybe not conventional wisdom because basically this is not what we think. This is not what we sort of think about when we think about deep neural networks. These are huge neural networks. Well, but they're still very shallow. And if you think about this, say you're playing a. Now here comes the point of the podcast where I want to whiteboard. Sorry, people who are listening to this. Say you're playing a three-dimensional game and you want to learn to that the same action, like the same action sort of means a thing in when you're at the top left of the screen, and it means the same thing in the bottom right of the screen. How then you need to do this spatial transformation where you basically move yourself, you put yourself in the position of this agent. And if you have two convolutional layers and two fully connected layers on top of this, that's just like not even nearly enough to do these complicated spatial transformations.
Hmm.
And if you actually need to plot a path to the end of the level, you need to figure out if you're going to go left or right. But in order to figure out if you're going to left or right, you need to follow sort of with your eyes which of the paths lead to the door. Um, you can't do that with these shadow networks. You're not nearly enough. And this is the kind of things you need in order to be able to learn any kind of general game playing ability. So, what's the solution? Complicated recurrent or attention based networks that can keep churning for a while before they make a decision. Maybe. I don't know.
Yeah, yeah, yeah. So probably some sort of temporal reasoning.
Yeah, yeah. It's really fascinating. There are these spiders, these jumping spiders, the portier spiders, that can navigate mazes. They stand still and look at them for a while, and then you sort of and then they can run through the maze and get to the end. And they must, because this has been systematically tested, they must be doing some kind of path calculation internally. And and then you sort of open one up and look at his brain, and it really ain't very big. so but it's the way it's the way it's represented. Somehow it is learned some kind of path planning mechanism, but you
Mhm.
can't do that with four layers of feed forward.
You actually looked into another fundamental thing, which is like introducing these inductive biases into networks. So on this game called Cells, you had something called the convoluted neural network,
Right.
and and it turned out that this network design learns faster and had better final performance than just
Right.
using, say, a feed-forward network. So I
Yeah.
thought that was pretty interesting that it does touch on this like larger issue of like what kind of inductive biases do we need to build into the network to take advantage of symmetries and things like this?
This is and this is something that basically now I think back to the debate between Gary Marcus and Jan LeCun, moderated by David Sharmas, that were held here at NYU a few years ago. which is very fascinating. I think that we need a lot of these inductive biases. We need to either construct them, or we need to construct them, or we need to learn them.
Hmm.
And I think that evolution is probably the way to learn them. We have a lot of neural architecture research going on, and I think I'm happy that we're seeing the resurgence of this area. It used to be called new revolution of topology, but that's now
Hmm.
neural architecture search, and it's it's a really useful sort of. I think this is part of the way forward, and even what seems like very very simple biases can make a huge difference. So this thing I talked about
Hmm.
before, where I mean, the paper you mentioned, what we did was simply enforcing a radial symmetry in the network, because the network had
Hmm.
inputs from 8 different directions, and it needed to react the same to to them. So we basically enforce it with weight sharing, and it worked very much better. Uh, and this wasn't a particular novel, a particular sort of even clever, I guess, but it's something that people have a sort of a resistance to doing, because it's considered like not the way to do. You want everything to be like to be learned from first principles, which is, I understand where that sentiment comes from, but at the same time, we've all read about the no free lunch theorem. We all know that all machine learning lead inductive biases. You
Hmm.
cannot learn without it, and if you with some simple biases you get much better results, why not? You should do it. You should just be honest and upfront about what biases you sort of put into your network.
Hmm.
We did recently, connecting back to the thing about third person and first person, we did this experiment where we basically just like took a third person game, um, translated it, so you basically have the agent in the center, rotated it so the agent's always facing up, and in some cases also cropped it so you only saw the area around the agent, and compared how well it generalized, and it generalized much, much, much better. So this wasn't
Hmm.
actually in the neural network. This was in the it's a piece of code, like a few lines of Python before the network input. So technically, maybe that was not the machine learning bias in the network, but you could have trained a neural network to do the same thing. It was just like easier to do this with a few lines of Python, and
Hmm.
this completely changes how well the learning can generalize.
Yeah, so I think maybe we could go to the next um, section. Well, so there's three sections, but maybe just in the interest of time, I wanted to go to this innovation section. So here, the high level goal is that, well, you don't have a defined goal, and the goal is to learn some agent which innovates.
Hmm.
Um, and one application that you worked on in this thesis is trying to come up with personalized racing tracks. Um, so based on someone's playing style, based on like some notion of fun, can you create novel racing tracks? So I
Yeah,
thought this was a really interesting idea, and you write in the thesis about how it was kind of new at the time, and you could see a lot of area for improvement there.
yeah. So then I spent like the next 13 years improving on it. Not quite. I never revisited
Hmm.
that particular setting. However, in the company that I co-founded, Model AI, we have an internal demo which actually does personalized racetrack evolution for for a little racing game, which we haven't released yet. But that's so it very much builds on that. But yeah, it was new at the time because people weren't thinking in those terms, as in like, what if you create not a game player but aspects of the game,
Hmm.
and it did get a lot of attention for that reason, and also a few comments early on. I've seen this again and again. I get comments saying, "What, you're only using? There's no method development. You're only using existing methods for a new thing. I don't like this paper. Vote for reject." Um, I've seen this like almost all my most influential papers have had some versions of that comment. which I think it's
Hmm.
so now I think it is a badge of honor. Like, oh, this is not like a machine learning advance. Oh, thank you, great. I must be writing a good paper that's going to have a big impact. So
Hmm.
because many people reviewing papers have an extremely narrow view about what an advance, what constitutes an advance. Um,
Hmm.
uh, yeah, so we built on this idea in different ways. One thing it did was introduce this idea of like procedural content generation as an AI research topic. I wasn't maybe not the first to do it. There's been a few other examples, but this was the paper that sort of got this ball rolling to some extent. Then yeah, the other early forerunners were people including Kate Compton and Gillian Smith at UC Santa Cruz, which is maybe the best game AI group in the world. Only because there are more of them. No, they're good too. But uh, this idea of like creating the track and to have not be easy or hard, but be have the right difficulty and be fun for a particular person. Sort of have a variation challenge, for example, and these are strange sort of fitness functions or strange sort of rewards to have. We built a lot on that and showed how this applies to a lot of different games, and lots of other people have taken this idea to lots of different game and game-like domains. And this is a lot of fun. We also sort of built an idea of modeling playing style so that you can sort of recreate it, and so that it transfers across different levels and so on. Which is, when you think about it, it's like learning an agent that can play in multiple different levels, but now you also need to be in the style of a particular human person. It's a hard problem. It's I guess it's called imitation learning these days. So yeah, this became. What do I want to say about this paper? Really, this was what sort of really launched my career, and
Yeah.
and almost everything I've done, 75% of everything I've done since has some intellectual depth to that paper.
So in this procedural content generation, there's definitely echoes of this problem. I was doing this thought experiment as I was reading this. Like, what if you had a really good generator, which could make a slightly harder version of a level for the current agent, and
Mhm.
then you train the agent on the slightly harder version, and
Mhm.
then you repeat the process. So then,
Yeah.
shouldn't in the limit you have an agent which could play arbitrarily hard environments?
Yeah. Um, it's a beautiful idea. I've attempted it many times. It always breaks down in some way. It's it, I have a bunch of like papers that are like sort of halfway there in various ways. I have like papers on generating games or game levels that are learnable in particular agents, um, or that are more challenging for weaker agents, and that stronger agents get higher results on it. Uh, the poet environment, also by the people at
Mm.
now OpenAI, formerly Uber AI, Joel Lehman, Ken Stanley, Jeff Clune, and some people I don't actually know in person. There's the poet sort of system builds very much on this idea as well, and it's I think that's a really really clever idea. They basically divide it up so that they have pairs of like agents and environments, and then each agent tries to get better at its environment, and then they can transfer over to other environments, and new environments are sort of spawned as offshoots of the existing environments to be where they are hard for existing agents, so they can move there. So it's a very distributed solution to doing this. Um,
Hmm.
we have a recent paper which recently renamed this in the review for another conference, but it also been an archive for a while. Um, it was desk rejected from HGuy, as was basically everything I submitted there recently. We call it generative playing networks. We don't use
Mm.
evolution at all. We use gradient based training to train a generator and a player. And the player is trying to, it's very simple, it's trying to play the environment as well as possible. The generator is more complicated because it uses, the agent is an actor critic. So it uses the critic part of the agent to figure out how good it thinks it is, and is trying to give it the right amount of challenge. Because you can always, in most sort of setups, it's easy to come up with an agent that will just like, oh no, with an environment that is impossible for the agent, and that's not interesting. So you need to have the right amount of challenge. And this system, the generative playing network system, is not super. It doesn't work super well, but it gives some interesting results. I think there's a lot to build on there.
Yeah, the other thing I was thinking of is, so in this simplified, or yeah, so in the setting of the thesis, what you do is you have this array which represents the racetrack. So nowadays, could you think about having some generative model of different environments and then
Oh yeah.
taking a latent representation and changing that instead of this?
Oh yeah, oh definitely. That's a very good idea. So basically, we've done that with a couple of different things. We've done it with levels
Oh,
of Super
cool.
Mario Bros. I mean, started for with like I did a paper not at all on games a few years ago. I was collaborating with Nasir Maman in my department and our PhD student Philip Bontrager on a security project. It This might have been the paper of mine that's gotten the most attention, very surprisingly. So Nasir and his friends and his colleagues have been sort of observing that fingerprint recognition systems in consumer devices such as phones only take a partial fingerprint, so they're kind of vulnerable. Um, and also, more strangely, some people just seem to have better fingerprints than others. Their fingerprints are better at unlocking phones, their own, and occasionally others.
Hmm.
And this is weird. So there must be some strange exploitable irregularities in the fingerprint recognizers. So we built a system to produce master prints, just like master keys. So fingerprints that would unlock many other people's devices. So we trained again on a public fingerprint database, and then we evolved the latent inputs again. Which when we did this first back in early 2016 or something, that was like a completely new thing. The paper wasn't published until 2018 because it got rejected by three AI conferences until it got rejected by NeurIPS, AAAI, and ICML. Until we sent it to the Best Conference of Biometrics, where it won a Best Paper Award, which is like the moral of the story is that people have very narrow sort of ideas about what constitutes an advancement in these conferences.
Mhm.
And um, it worked extremely well. We were able to find out fingerprints that could unlock it. It could authorize as 22% of all of the 5,000 people in this data set using industry standard settings, which apparently shocked a lot of people in the security industry. But then we used that same approach to game levels, us and other collaborators, and it works extremely well. So you can definitely train generative model and then search in latent space. The problem, of course, is that your innovation becomes limited because you are sort of searching within the convex hull of the data you trained on. That's one
Mm.
problem.
I see.
And the other problem, because there's been a number of ideas about using machine learning, using various forms of supervised or self-supervised, unsupervised learning to train an existing levels to create new game levels, or existing game content to create new game content. The other problem, which is more fundamental, is that for most games, you don't have enough content to train on. And in particular, if you want to make a content generator that works for a new game, like yes, there are lots of if you manage to get like access to the data storage of the Super Mario Maker, um, then you could drink straight from the firehouse and basically train on hundreds of thousands or millions of levels. But for most games, you have maybe 5 levels to train on. So
Mhm. I see. And then it seems like the other thing is that if you evolve some latent representation, then it might not actually map back um, like to an actual playable level.
yeah,
Yeah.
it is indeed true. We did try to address this with a paper that we put out last year that's being presented this year at one of the conferences in the field. The conferences are not, yeah. Well, we train, we what's the exact title? Bootstrapping self-attention generative adversarial networks for game level generation. The idea we have there, because as you very much observe, like the generative model will learn a bunch of interesting regularities represent the visual aesthetics of the level, but it will not learn what makes it playable in general.
Hmm.
So what we did there was that we tried to attack this problem and the problem of not having enough training data with the idea that you train it on just a few levels and then you sort of start producing levels and you check them for playability. And anything that's sufficiently novel and is actually playable, you add it back into the training data and then you keep training on it. So you're sort of bootstrapping it. So you're producing your own training data, which in general, producing your own training data is terrible because garbage in, garbage out. But games are a very different domain than, for example, generating images, because for most types of game content, you have playability criteria that you need to adhere to, and therefore you can actually check them using you can check playability using various agents. And it's okay if your playability check is overly strict, because you can generate so much content anyway. Yeah, yeah. As you say, this is a little bit taking these old ideas from 2007 and combining them with GANs. And hey, you have new stuff.
I wanted to save some time to talk about current work, but I think throughout the conversation we've touched on different things that you're working on. But yeah, did you maybe want to highlight or outline what you're looking at going forward?
One thing I'd like to mention was, because I was talking about, because of two comments in the past. One is that I'm drawn to things that don't make sense, and one is that I was saying that the neural networks that we train are far too small to learn general playing behavior. I'd like to contradict myself, one of my favorite things to do, by pointing out the paper we published at AMAS last year, which is called Playing Atari with Six Neurons, which is just what it says. It is playing Atari with six neurons. We use tiny, tiny, tiny neural network coupled
Mhm.
with an input representation where um, we basically save up a lot of. We basically find prototypical states, and then we have a way of encoding prototypical visual input states, and then we have a way of encoding how close the input is to the different uh, to different visual scenes we've seen before. So we're sort of creating a space of like relative to things that we've seen before, the visual input you get now, where is it? And then with this sort of strange representation, just by transforming it this way, we can play. And the actual policy part of playing a Atari game turns out to be extremely simple, because these games are simple. Playing them isn't that hard. Um,
Mhm.
and all of these neural networks tend to be doing is like visual processing, and they do it extremely badly, because they can't generalize to new levels. So this is actually it is basically a contradiction. It's not entirely contradicting what I said before. It's backing up my statement that training deep neural networks via reinforcement learning to play games with third person views from pixels is a fundamentally flawed thing that is not working. It's broken,
Mhm.
and we all need to face up to how extremely deep these problems are, and start working on how can we actually make this work for real. Um, yeah. So this paper also got rejected from from several top conferences until it got
Wow.
into AMOS. That's what happens with good papers. So that's one thing that keeps puzzling me, and I keep thinking about how could we actually learn to actually play the game instead of whatever, and also related to this, what are these deep networks learning? They're not learning anything useful, or they're learning something very narrow. That's one thing that keeps me going, and the other is procedural content generation through machine learning. How can we deal with that? How can we combine supervised and self-supervised learning with various kind of search optimization strategies to learn to produce game content. One thing that I really want to do, but I haven't really figured out how to do it properly yet, um, is to be able to train on multiple different games. Say you have 10 different platform games and they have 10 levels each. And you both train it in all these levels, and you somehow encode what mechanics are relevant in these games. In this game, you can shoot. In this game, you can jump. In this game, you can climb. And then you ask it to produce levels for a new game you've never seen before, but which has some other combination of mechanics. And it draws on the general representation it has to produce new content. Um, I have not seen this happen, and I don't really know how to do it. It probably includes like special magic, and you have to sacrifice you have to sacrifice a hen while walking backwards around a fire or something, but or it involves deep learning, which is essentially the same thing. But it's that's one thing that I really want to do. I also want some vacation. That's another thing, but that's I don't think
Yeah,
deep
yeah.
learning. I don't think deep learning is going to help me with that.
Yeah. Well, you come back from vacation, you have more ideas. So, yeah, this has been really good going back, and I personally found it really interesting. First of all, that you kind of have been working on related things for your entire career, and it
Yeah,
was cool to see that there's connections.
yeah. No, I think that the same things keep me going, and
Mhm.
I think I suppose it's true for others as well. You feel like you had so many ideas that you never could properly explore, and you go back to them, and this time you try to do it right. It's and because that's how research is. That's what it's like. You're just never finished.